If you were to calculate the sample variance, s squared, by dividing the sum of squares by n minus 1, which is actually the formula that we do use, the average of all sample variances would be, in this case, it is b equals to the population variance. The whole idea here is that we're using the sample variance, to try and estimate the population variance. Anytime we take samples in statistics, it's not because we're particularly interested specifically what's happening within that sample. It's that we don't have the option of, for whatever reason, we don't have the option of directly measuring the population. Very often, we want to have a look at how much variability there is within a population. So, to get the population variability, we satisfy ourselves with measuring the sample variability, but unfortunately samples don't often show as much variation as populations do. So in order to correct for that, we don't use the exact same formula that we would for the population, because we recognize that the sample variance is often too small. In order to give it a boost, to make it bigger, we perform this correction. So we divide by, not n, but by the degrees of freedom, which are n minus 1. What this does is it makes the entire fraction worth more. And because this is worth more, it adjusts our estimate. Instead of our estimate being too low, where the sample variance underestimates the population variance, it corrects and we get an estimate which is equals to the population variance. Now that doesn't mean that every sample variance is equals to the population variance. What it means is that if you were to repeatedly take samples and measure their variance, some of them will be too high, some of them will be too low, but in the end, once you average all sample variances, they will in fact be equal to the population variance.